note, you guys? I didn't realize this. No, I guess I'm stuck. I'm sorry, in my head, I'm dividing both sides by x. And I'm saying I'm coming so close to viewing this dE as a homogeneous dE. But I guess I'm messing up on the very first time. I was just in my head trying to see if I could solve this dE in a different way. All right, so if you want another example, why don't you take a peek at this? X, y, y prime minus y squared plus x squared. So with this dE, shoot, question, is it really removed? So I'm asking a simple question before we solve it. Does it seem to fit that pattern, number 4 over there? Yes. Yeah, I think it does. I think if I send this term right here to the right-hand side of the equal sign, force this to be y by dividing both sides by y, is Bernoulli. I will not go that far. I kind of like the way it's written now. The only thing I can see significant is maybe getting rid of the x up front. I will. So multiply both sides by 1 over x. I'll commit to my substitution. I'll allow you to be, gosh, I hear my voice too much again. But that necessarily implies du dx is going to be this in terms of dy dx. And now, yes, sir.
With the on the right, the minus x, would it be minus x cubed? Or, oh, my bad, sorry.
Yeah, I'm just not there integrating it. I'm just dividing both sides by x.
Sorry, I thought there was negative 2, my bad.
And everybody committing to the substitution. Ay, ay, ay. Does that give me a u? I misspoke, sorry. I meant to say du dx. Is it a minus 2 over x times u being equal to a negative 2x? You know, the lonely feeling I keep telling you about that I experience. Is that okay? If it is okay, can we dive in and use an integrating factor? So we're going to choose an integrating factor to be, is that e to the negative 2 integral of 1 over x with respect to x? Or shall we say, is that a 1 over x? By the way, you guys, can I make the simple assumption that x is strictly positive? And I maintain that multiplying both sides by this integrating factor, I have the derivative with respect to x of my u over x squared being equal to negative 2 over x. Shoot, you guys, life's a piece of cake, isn't it? Oh, I forgot y's original name. Is it y squared? Oh, you know what? I forgot I made the stipulation x is strictly positive.
Yeah.
So I guess I didn't mean the absolute values. I forgot.
Are you ambidextrous? Because I just saw you write with the left hand and wipe with the right.
Yeah, how long did it take you to learn how to do that?
I didn't know I did it.
You don't even know you do that? You
No,
can
Professor,
erase and
Professor
you can write.
Wiley Barron, when I was first hired, had to evaluate me.
Yeah.
And she said, do you understand what you're doing? I said, no, I never realized that.
That's awesome.
I had a graduate professor who insisted on only teaching 50-minute classes. And the classroom he always insisted teaching it had a chalkboard that started right there at the corner and wrapped continuously around these 3 walls. He was right-handed. He'd always start there, and with his right hand right, and with his left hand he'd erase. And at the end of the 50 minutes, every time he'd be at that corner, but there'd be nothing on the board.
That's evil. I mean, his body would be right in the way of everything he's writing.
That's my whole point. Yes. You guys okay? Oh, you guys, I can't believe I feel so free. I've got so much time. I can add to my list. Now, everybody, let's just suppose I had a differential equation of this form. Some function in two variables, dx, plus some function in two variables, dy being equal to 0. If it's the case that the partial of m with respect to y is equal to the partial of m with respect to x, then I'll subclassify this as an exact DE. And I have to confess, there are many times for which this condition is not being met, but I come so close. In situations like that, you will see, I hope today, oh definitely today, in cases like that, I'll be able to multiply both sides by special integrate factor to transform the DE into one that is indeed exact. But can I talk about the theory behind this? Because this looks just too different from the type of DE we're solving so far. So, everybody. Suppose I have some function phi in terms of x and y that's equal to a constant. In other words, I got even maybe an implicit relationship between x and y in such a way that if I isolate a constant on one side of the equal sign, I get a function in x and y on the other side. If I can express a function in this fashion, shoot, I gotta stop. This might be something with which you're not familiar. What I'm about to spout off is something from Math 32, and I know it's not a prerequisite for the course, so let me just try to do some hand waving so you can see what this is. If I had a surface in 3 space, like this, hold it, like this. I want you to plant your feet right here. Now, as you move on the surface, how are the z values going up, changing?
Depends on which way you're moving.
Thank you. You have no clue. Depends on which way you're moving. Well, here's the x-axis. Here's the y-axis. Then I think if I'm moving in the x direction, I think the z-values are going to decrease. I think planting my feet right here, if I'm going to move in the y direction, looks like the z-values are going to increase. And so sometimes I might want to talk about just moving in an arbitrary direction and see how z changes. I'm going to take into consideration both those components. So when it comes to function phi in 2 variables, thinking of z being equal to that, I can treat that as a function of 2 variables. But I also sometimes might want to consider the total differential for those z values. And I think if I differentiate the right-hand side, I'm simply going to get 0. It's just that my total differential I'll define as being, I don't know, taking my function phi and partially differentiating with respect to x, and then move slightly in the x direction. And add to that how phi is changing, moving in the y direction, and moving a small distance in the y direction. And I maintain this looks just like my equation over there. It looks like my function big M in terms of x and y, dx, plus my function big N in terms of x and y, dy, being set equal to 0. By the way, what I have in parentheses there is really how to actually solve this DE. I've not talked about solving a DE yet. I'm just playing around with total differentials. So do you guys remember this? Shoot, I'm embarrassing myself. I can spell it as French. Do you remember Clairaut's theorem? Yeah. If I got continuity for all those partials, even the mixed partials, it is a case that for any function f, its partial with respect to x, then with respect to y, is equal to its partial with respect to y, and then with respect to x. Those mixed partials are equal to each other. So if I got continuity all over the place, then I think that means that this partial with respect to x, when I partially differentiate with respect to y, is going to give me the same darn thing as this partial respect to y, is then partially differentiated with respect to x. Or shall I say, if I think of m as phi sub x, doesn't that just mean m sub y is equal to n sub x? So for me to check exactness, I am going to check this condition. And then I'm going to try to find that function phi that solves this equation. And sometimes I give that function phi a name. I sometimes refer to it as my potential function. Those of you who are Math 32 graduates, you did this all the time back in Math 32. Now, I'm exaggerating, maybe not all the time, but you did come up with these functions. So everybody, this is a free day from here on out. I'm just revisiting Math 32. Here too, so I don't waste your time, you guys, I don't want to make these examples up out of thin air. I know I created some. All right, just need to find them. Ah, I do have some. Beautiful. So how about looking at a differential equation as such? So, in solving this differential equation, I certainly would suggest that any of my other techniques, you guys, doesn't even close to being viable here. Certainly not first order linear. I got y's all over the place. Therefore, it's not going to be close to Bernoulli. I just checked, I can't separate variables. Certainly, that homogeneous type substitution of letting u equal to y over x doesn't even come close to applying here. So, I give up. I'll treat this as an exact DE. In treating as an exact DE, let me separate. Let me write it out with an alternative standard form over there. And rewrite it. Let's give you this. Is that a 2y minus x cosine y dx? Did I just make another mistake? Jeepers, I sure did. My goodness. Does that give me a sine of y dx? Minus a 2y minus x cosine y dy being equal to 0. I'll even go so far as to bring in the subtraction operation. I now have this function I'll call m dx plus this function I'll call my n dy be set equal to 0. Let's check for exactness. In checking for exactness, I'm going to take my function m, partially differentiate with respect to y and see what I get. Oh, gee, isn't that just straightforwardly the cosine of y? But if I take my function n and partially differentiate with respect to the variable x, okay, guys, I'm done. I get the same thing. So I guess I have exactness. Since I do have exactness, let's solve. So to solve this differential equation, here's my solution. Where I maintain that when you take a peek at that function m, this is the partial for phi with respect to x. And when you take a peek at the n, shoot, you guys hold on, I'm just walking too fast. I've got a solution of this form right here, whose partial with respect to x I said is equal to m, jeepers, and whose partial with respect to y is equal to my n. But you guys, I blew it in a sense, I really want the solution phi, so how do I generate my solution phi from here? Yeah, I think I'm going to integrate. Or shall we say we're going to undo a partial derivative. If I want to get phi back, undoing the partial derivative, phi partial with respect to x is my m. And so phi itself is going to be 1. I heard that. Say with confidence. So x sine 1. Oh, shoot, we forgot. There's a constant integration. Oh, but but shoot, I think it could be bigger than just a constant of integration. I think it could be something as big as a function in the variable y. Okay, I'll change it. I guess I should be adding in here some function solely in terms of the variable y. I'll give it a name, I'll call it h. But I think over here, since the partial with respect to the variable y is my end function, I don't remember what it is. Is that an x cosine? Oh, I need more room. Is that a y? Minus 2y? Oh no, they're not the same. Shoot. But you know what? We can force them to be the same. For this equation down here, imagine what would happen if I partially differentiated this phi with respect to the variable y. Isn't that just simply going to give me my, gosh, is that an x cosine of y plus h prime of y? However, I maintain, that was my red pen, what you see inside this big circle is just a partial phi with respect to y. What you see inside this circle right here is oh look at that, also the partial phi with respect to y. So if I equate those two partials, you guys, doesn't that trivially just tell me that h prime of y
Is equal to,
is negative 2y?
yeah.
Or shall I say hy is just anybody? It's a negative y squared. Did you hear about the constant? Okay, you do. Don't go put it in. Personally, I think it doesn't make any difference, because if I don't put my constant integration in, when I come back and list my solution, I'm just going to equate it to another constant. That's what I'm saying. It doesn't matter if you include constant here or not. So, everybody, I think we have a solution to a DE. I think, number one, I now know what phi is, because check this out. My line over here says that phi, as a function of two variables, is merely going to be x sine of y. Is that a plus h of y, which I just found to be this, is equal to a constant. That is my solution. Oh shoot, look at this example. I didn't notice it. And this example clearly is not algebraically solvable for y. I have no algebraic technique for isolating y, since this is embedded in both this algebraic and this transcendental function. I'm really stuck. I cannot isolate. You guys, that was a mouthful. Did you get that? Sir?
It seemed pretty nice that like it really worked out easily. Is that a common thing when you find that they are
Yes.
exact?
Yeah, the only obstacle you're going to have is that sometimes this condition is not that, but it comes so close. And that's the only thing you have to worry about. Certainly if you're going to try to find this potential function, these partials will end up being maybe not equal to each other, but you'll be able to finagle them to find out what the h prime of y is going to be. Or you'll force, in other words, this to be equal to what's missing over here. Well, if that is okay, you guys, 10 minutes. Do you think I can sneak in one more example?
Sure.
I'll stop talking. Oh, can I just pick and choose something really nice? Ooh, that looks really nice. You know what? This looks familiar. I must have grabbed this from an exam I wrote in the past. Well, you guys, just because of the way I wrote the differential equation, I suppose the immediate thing you're going to do is see if it's exact. Just see if it's exact. Let's you and I take our function m, compute its partial respect to y, see what I get? In this particular case. Oi, 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 here too, you guys always make me do the work. It is a product. So I did first. Times the derivative of the second with respect to y, plus the second times the derivative of the first. And if I differentiate my n with respect to x, I get, holy cow, not even close. Shoot. I guess it's not exact. So, if it's not exact, talk you into forcing an integrating factor to exist. Number one, if it ends up being the case that when you look at this difference, this ends up being a function solely in terms of variable x, then there's a guarantee that this is going to be an integrating factor that transforms the original dE into one that is indeed exact. Here's the integrating factor. It's going to be the form I of x being equal to, oh shoot, you've seen this already. However, if this particular algebraic expression ends up being a function solely in terms of variable y, then necessarily this integrating factor in terms of variable y, if you're to multiply on both sides, will transform the original dE, yet again, into one that's exact. But let's look at it. Now I have to confess, you guys are doing a little hand wave and beating the clock. I'm saying, oh, you're guaranteed it's going to transform d into one exact, and I haven't proven that. But all you have to do is multiply both sides, even in the general setting here, and it works. So, let's see. Let's see if I can panic and just transform my d over here into one that is exact. If I take a peek at this difference right here, you guys, doesn't that just simply give me this? I don't know what it gives me, jeepers. Is that a 2x minus 2x? And then a 2x natural log of product. And if I divide this difference by n, it's going to give me this. So question, I want a yes or no answer. Is that a function solely in terms of variable x? No, shoot, it's not. So I guess I wasn't able to transform that. What about checking out this difference and dividing by n? I think that's going to give me 2x natural log of the product all over my n, which in this case is going to be a 2xy natural log xy plus xy. What does that look like? Does anything cancel?
Natural log of xy and the 2x.
I'm nervous about the natural log because it's only just a factor in the first term.
Oh, yeah.
So the x is canceling.
X's.
I'm up with this. Oh, did I forget my 2? Jeepers. So question, am I able to transform that into a function solely in terms of the variable y? Uh-oh, hold it, you guys. Sorry, it's something else I just did. See this y? The magic to transform the natural log of y? I have no idea how. Harry Potter mathematics stuff. You guys, I'm serious with my question. I don't have the answer yet. Can I transform this into a function solely in terms of y? I don't see it. I think I'm stuck.
Okay.
I don't think either one of these works. So I think I cannot multiply both sides by an integrating factor in this example to transform the original dE into one that's exact. You guys, I just blew my time on the clock. That leaves you with 5 minutes. I don't think I have enough time for another example. Can we stop? However, no, I did not. That's one reason why I stopped a little early. I know I did not create a homework assignment.
As of an announcement.
So,
What's that?
You say shoot just as many times as you say jeepers.
Do I really?
At least according to this one, I added a few more of
How nice somebody listens to
your
me.
best phrases to the count. And you say shoot 10 times. You said jeepers 10 times.
Is that making your test or your analysis a little more comfortable?
I'm adding them in. They're individually part of it.
So, what's going to be covered on the test, or is everything that we learn through tomorrow going to be on the test, or?
Yes, definitely.
Okay. What about what we take on Wednesday? Will that be omitted?
Definitely not.
Okay.
I'd also like to say I'm not going to stop you guys today, but please do the homework
Yeah.
and tell me whether it was hard or not.
You guys, I'm not gonna actually solve or give you the exercise tonight on exact these. I'd rather spend more time. That's okay.
Okay.
So Brad, just so you get this straight, you asked,
Yeah.